Hello and welcome. My apologies for our technical difficulties here at the beginning. It's been a little bit since our last webinar, I guess, since last September. So welcome. I want to thank everyone for joining us today. My name is Colleen Dunn, and I am the sales coordinator here at TechX Corporation. We have today is Dr. Tom Jenkins, who has been with us a very long time, and he is going to be talking about advanced issues in PIC-MCC modeling of capacitively coupled plasmas. This webinar is going to focus on VSim 12. VSim is our flagship product here at TechX Corporation, and VSim 12 was released on September 20th. More information on all of the capabilities that are found in VSim 12, as well as in the software in general, can be found on our website, and there is a link right there if you would like to get more detailed information. We also had, every year we have what's called the TechX Worldwide Simulation Summit, and that this past year was September 21st through 22nd. Many of the webinars and presentations that we did last September were focused on VSim 12. So I recommend visiting our YouTube channel if you would like to watch some of those and you can get more information. We have, after today, what's coming up next is we actually have 12.1, a minor release of VSim is coming up. We are scheduling that for February 15th. That is the plan at this time. And it includes many, many improvements that are based on customer feedback from all of you who let us know the best ways that we can improve our products to enable more of the capabilities that you need. There is going to be an example in VSim 12, a template essentially that you as a user can learn from to set up your simulations, and that is going to be the example, featured in VSim, the release that is coming on February 15th. We do have another webinar coming up as well on inductively coupled plasma modeling. We are very close. We don't have a date yet on when that capability or when the webinar is going to be available for you, but we will make an announcement through our email and let you all know. So on that note, thank you all so much for joining us today. And Tom, I believe I'm going to pass it over to you now.
Thank you very much, Colleen. Fiddle with my Zoom windows here. Okay. All right, so I will be talking today about capacitively coupled plasma modeling using VSim. Some of the things that we have learned and things that we recommend based on the work we've done here at TechX. I want to give you a quick introduction to myself before I begin. I've been at TechX for 13 years now, coming before that from Princeton Plasma Physics Laboratory and University of Wisconsin-Madison, where I did my PhD and my postdoc, respectively. So my background is in both particle simulation and radio frequency wave modeling, actually. So some of my current research interests focus on various aspects of that, RF sheaths, impurity sputtering, and so on and so forth. But for purposes of this talk, we'll focus on the last bullet point here, which is particle and cell Monte-Carlo-Collision modeling of low temperature plasmas. And I'll point out also that I'll post the slides for this talk on my website, which the address is here, and I will provide that address again at the end of the talk if that's of interest to you and you haven't quite copied it down from the bottom here. All right. So a brief outline of my talk about the physics of CCPs and about some of the benchmarks that have been published in the scientific literature for verifying that your code or my code or anybody's code can actually model these kinds of plasma discharges. And I'll talk about some of the work we've done to verify VSim's capability to do CCP discharges. So what is a capacitively coupled plasma? Basically, in the most generic sense, I think of it as neutral gas in a box, and I'm going to put some electrodes on the sides of the box and couple some RF power through into the gas sufficient to ionize it and create a weakly ionized plasma. And of course, when you do that, particles immediately want to diffuse out away from one another and into the sides of the box and leave. So if we want to sustain a discharge, we need to be putting in enough power that the rate of loss to the wall is balanced by the rate of ionization in the bulk plasma. When you create such a plasma, you have a flux of particles to the wall, and in industrial applications, it's very common that you will tailor the parameters of your discharge. What is your feedstock gas? What is your power that you're coupling in, and what frequency, and so on and so forth, in a way that tailors the distribution of particles hitting the wall. You might want a specific energy, you might want a specific angular distribution, you might want some kind of physical interaction with your wall or with some substrate that you put just in front of your wall so that you can manipulate that surface. Maybe you're doing an etching process, maybe you're implanting ions in the material, or perhaps you're doing a thin film coating, whatever it might be. That you tune the properties of your plasma discharge in a way that gives you the surface interaction that you want. And this, of course, requires us to understand very well the properties of the steady state plasma discharge so that we get the thing that we want. And the physics of these discharges can be pretty complicated. I've got here a plot of a simple one-dimensional discharge that we'll be talking about a fair bit in this talk. We can look at an electrostatic potential profile, which I've got on the top left here. We can also look at the ion density in red, the electron density in the blue. And over here on the right, I've got a plot of the phase space. I've slowed down the electrons by a factor of 100 so that both of the phase space plots can be in the same window. But there's a couple of physics features here that I can point out as being important to the capacitively coupled discharge. One of them is that the electrons, because they're much lighter than the ions, they're much more mobile. And so they can see the electrons here in blue clustering toward the center of the domain because that's where the potential is pushing them. We've formed sheaths which confine the electrons after a sufficient number of them have been lost to set up a charge imbalance. But because the electrons are so much more mobile, they're going to be highly responsive to the potential, but the ions will not be. So I'm going to now advance this 1/4 of the period of the RF oscillation on the electrode, and we'll see what happens. What you see is that the sheath on the right has now collapsed. There's very little potential gradient over there, and the electrons have been pushed over to the far right side. And so we get a big impact of electrons hitting the wall. We also have these filamentary structures that are showing up on the left in the ion phase space. You can see them on the right as well. These are from ionization. And what you'll see when I advance the slide again, as these electrons slosh over to the right-hand side of the domain, they're going to ionize the background gas, create a population of slow ions that, as the electrons retreat from them, those slow ions will fall down the sheath and into the right-hand wall. So there they go. They've gone back to the middle. You can see the filamentary structure that's been created. And because of the positive velocity that we see in the phase space here, these ions will move to the right, but they will also move upward as they accelerate toward the wall because of this sheath. We have other collision processes in this discharge as well, elastic collisions and charge exchange and excitation and such. And those act as effectively as a damping coefficient on the diffusion in some sense. They will slow the diffusion of particles outward from the center toward the wall. And you can imagine that if we had very highly collisional processes going on in the center here, that it would take a while for a particle to move from the center to the wall. And so then we get to the 3/4 of a phase period, and now the electrons are off to the left, they're hitting the wall over there, and it's just the same as we had on the right. So in a quasi-steady state for this discharge, electrons basically slosh back and forth very rapidly in response to the oscillating electrode potential, and you get kind of bursty behavior of how the electrons hit the walls. But the ions, because they're heavy and slow, don't see that motion. They basically see a steady state DC potential that's created by the time average of this oscillating electron plus wall potential effect. And we saw these filamentary structures, and you can imagine that as these ions hit the wall, that the distribution of energies and angles that they'll come in at will be interesting looking based on what we see here. And I've got a plot of that. This is, in some sense, the plot of interest for you if you were looking to do plasma processing with the CCP discharge. We can see that we have various spikes in the impact energy. We have a pretty broad distribution of impact energies on the wall. And for a given processing, for a given plasma process, that may or may not be what we want. We might tune the discharge to get a more monoenergetic kind of distribution striking the wall. Or we might tune it to get a broader and less spiky kind of behavior if we were just going for a coating kind of effect on the substrate. In any case, we can tune the properties of the discharge in a way that gives us the surface effects that we want. And I should also mention that we can look at the angular distribution of incident particles. If we were doing an etching type application, for instance, digging out a trench on the surface of the substrate, we would not be interested in particles coming in with a very large angle here because they'll cut out the sides of our trench rather than cutting out the bottom in the way that we hope for. So for these discharges, we can make plots of the energy and angle distribution function. You can see the spikes that I showed in the previous plot, but now separated out by angular impact as well. And we can tune the discharge to optimize these kinds of plots as well. So looking more generally now, what is it that sets the steady state physics of a capacitively coupled discharge? We've got a number of inputs. We've got how much RF power we're putting in, what frequency is it? Does that frequency compare with the ion response, plasma frequency and such? What is the shape of our waveform? People use dual frequency waveforms for tuning and sometimes more complicated waveform shapes as well. It's also a strong function of the background gas. We are going to ionize that gas to create the ions, and so the kinds of material we start from has a lot to say about the discharge we get. And the collisions that influence that gas, electron neutral, ion neutral, how does the charge exchange work, how does the ionization work, will also contribute to the steady state profiles that we get. And also the chemistry, that's probably obvious. If I have a discharge in air, it's going to be vastly more complicated than if I have a discharge in argon. And then lastly, you could look at the surface properties of your device as well. If your chamber has a complex geometric structure, it's going to be different than if it's just a planar capacitive kind of behavior. Do you have secondary emission of electrons as particles hit the walls? Do you have sputtering as particles hit the walls, etc.? And the thing about all these parameters is that they're very tightly coupled, that if I'm going to make a small change in one of them, then that will kind of propagate through. If I change my ionization source by a little bit, then suddenly I have more ions and the transport outward of particles is different. The collision rates might be different because the local densities are different and so on. So when we're modeling these things, that can create problems. If I have one little thing wrong, that little thing is connected to 7 other things that are also going to be slightly wrong because of it, and then I don't get the right answer. So there's the salient question then. How do we build confidence in our numerical models of capacitively coupled discharges? There's been a number of benchmarks proposed in the literature by Miles Turner back in 2013 that are trying to tackle this problem. Essentially, the goal of these benchmarks is to create problems that everybody can do, that everybody can run their code and test against the benchmark results and see if you're able to get agreement with those benchmark results in some meaningful sense. And in order to make it a problem that everybody can do, it's in some sense simple. That's probably a misnomer in some sense, but it's certainly less complicated than things you might do. The geometry is one-dimensional, plasma is unmagnetized, single ion species with helium, and so the chemistry is fairly simple. There's a specified number of collision processes with given cross sections. There's no wall interactions and so on and so forth. But essentially, the goal is to give us a range of gas pressures and gas discharges that we can simulate, can see if our code can do it. And we can compare the steady state ion density profile, because as you saw earlier, that's fairly static in time and not sensitive to the RF effects that we're bringing in through the electrodes. We're going to compare that profile with the Turner results and see how we do. And Turner's provided a statistically rigorous chi-squared benchmark for testing any other person's results against his results. And I'll talk a bit more about that on the next slide. So this is the Turner case 1 benchmark, low pressure. There is room temperature helium and a 450 volt RF electrode at 13.56 megahertz being dropped across a 6.7 centimeter box. And we create a plasma, we sustain the discharge, we look at the ion density profile and see what we get. These are Turner's results for the ion density profile in the bottom left, and 5 codes that ran the benchmark and were able to demonstrate agreement with the benchmark results. VSim is another code that can do that. In this right plot here, I've shown the Turner benchmark result, which is in the red. And then with each grid point, there's in this plot, for each X value, Turner will also provide a statistical standard deviation of the data, so that if I do n bar, the Turner provides plus or minus the standard deviation. I get a window of density values that if my code falls within there, then I'm probably doing the right thing. This chi-squared metric essentially takes the difference between my code and Turner's code, puts it over the standard deviation Turner provides, squares it, and adds it up for every grid point left to right. And you can see that if my code gives a result that's bigger than 1 standard deviation, I'm going to square that term and it's going to be bigger than 1, and it'll contribute more to this sum. If my deviation is less than 1 standard deviation, I'll square it and it'll get smaller, and it will contribute only a little bit in this sum. So Turner tells us what these results should be at the 95 and 99% confidence intervals for agreeing with what he's specified. That was probably way more statistics than anybody wanted to hear today. So does VSim pass this benchmark? Yes, it does. Are there subtleties? Also, yes. The main subtlety I want to talk about is that Turner does not require us to do correct physics. Turner requires us to do matching physics. And not only matching physics, but matching numerical modeling choices. And if we do the same things that Turner does, we should agree with the results Turner gets. That's how we like to think of this as working. But that has very little to say about the physics per se, in some sense. I'll explain what I mean here. So in our discharge, we have ionization collisions. And what do those look like? And Turner tells us what the cross-section should be. For a given energy, we have a given cross-section sigma that's associated with that interaction process. But what do we do with the reaction products? I mean, the conventional approach you take in PIC-MCC, and there are other approaches, but this one is very common, is by Vahidi and Surendra, where we essentially look at an electron neutral interaction in the rest frame of the neutral. The electron comes in, hits the neutral, creates another electron and an ion, and then we send the discharge products off somewhere. In the Vahidi surrender approach, this angle that we send the products off at is a function of incident energy, and we get larger energy, meaning larger deflections. We scatter off randomly in the azimuthal angle going around the incident unit vector because the electron momentum is very small relative to the neutral momentum that we're in the frame of. And when we take this collision and we put it into the Turner problem in VSim, we do not agree with Turner's results. We get a density that's low by about 7%. And so this is kind of illustrative of a broader problem that you get when you're trying to match benchmarks like this. You run your code and you get this result, and how do you know what the problem is? Maybe your ionization is wrong. You're not creating enough particles, and so you get this profile that's low here. Maybe you have a different collision process, elastic electron ion neutral process or something that's wrong, that's got a collision rate that's too low, and so you get more outward diffusion than you should have, and so then your ion profile is also low. So there could be any number of things causing this disparity, and getting the benchmark right requires you to basically dig into every single process: elastic electron neutral, elastic ion neutral, charge exchange, excitation, and everything associated with your collisions, everything associated with your field solves, and so on and so forth, and figure out whether you're doing that thing in a way that's consistent with the benchmark. Turns out that Turner is, in this case, doing a different ionization process that strictly conserves momentum and energy, moves to the center of mass frame of the electron and the neutral, and scatters these electrons isotropically in the center of mass frame with matching energies. And this is not necessarily physical, but it is deterministic up to the random scattering angles. It's a thing that my code can do and your code can do, and if we can all do that and then compare against Turner, then we can have some meaningful comparison go on with the benchmark results. Another issue that comes in is with the physics that we include in VSim. Turner specifies the masses of the particles in his benchmark to 3 decimal places after the electrons and 2 decimal places for the ions, sets the neutral mass equal to the ion mass, and away you go. In VSim, we of course use the best known value for the electron mass and for the masses of various ions and neutrals. And so we disagree in the 4th decimal place. We have a relative change in mass by less than 0.5%. But if we run the Turner benchmark using the default VSim masses, we will not get very good agreement. You can see that here our chi-squared is within Turner's 95% confidence interval, but not within not within the 99. Oh, I said that backwards. Not within the 99% confidence interval, but only not within the 95. And so the takeaway here is that you can do correct physics with your code, but the correct physics may not be what's needed to match the benchmark. What you need is matching physics. And the third thing that we've looked at, the standard particle in cell rotation, where you deposit particles to the grid, you compute a charge density. From the charge density, you solve a Poisson equation to get the potential. From the potential, you compute an electric field. And then you have a choice. You can either take this electric field that exists on the grid edges in between the grid points, and you can interpolate it to the grid points to get a node electric field and push the particles with that field. Or you can just push the particles with the edge electric field that you got in this step. And depending on which thing Turner did will depend on how good of agreement you get with the benchmark. For us, we found that we get better agreement with Turner. when we use these edge fields to push the particles, although that's not what's conventionally done in a PIC-MCC code. So what does it mean to actually pass these benchmarks? Does it mean that your code is able to do all kinds of fun and interesting low temperature plasma discharges? Maybe, but not necessarily. That's not the thing the benchmark is trying to do. What the benchmark is trying to illustrate is that very basic code features work well together and give consistent results that agree with accepted modeling practices in a broad range of physics regimes. So we can push particles in response to electric fields. We can do a field solve from a given charge distribution. And we can model very detailed collision processes of ionization and then elastic scattering, charge exchange, and such like. And that these different modular pieces of the code all work together in a way that, in some sense, agrees with things that people believe to be correct. So the mathematicians would say that there are necessary but not sufficient conditions for things to be proven. And these benchmarks are a bit that way, that if we can pass the benchmarks, then we have confidence that at least some parts of our code work well and can do the detailed physics that our customers are interested in using for their more complex discharge models. We feel confident about that. So wrap up, the physics of capacitively coupled plasmas is very complicated, and that opens the door to lots of uses in industry and etching and thin film coating and such. If we're going to model those things using VSim or using some other software, we need to pay careful attention to the underlying physics and make sure that we're getting all the details right in a way that allows us to make good predictions of what our experiments should do. The benchmarks published by Turner in 2013 are a good starting point for verifying that your code is able to do that detailed physics modeling, and we have confidence and have shown that VSim is able to satisfy benchmarks that Turner's provided that use our new reactions framework. And I should point out that this is a change to our existing Turner example that we've had, which used our old reactions framework that had less functionality. The new Turner example that we will be including in the 12.1 release will make full use of our new reactions framework and have greater capability to do different discharges of interest to our customers. And successful benchmarking activities of this sort are the kinds of things we're interested in at TechX, to build confidence in our software and to ensure that it can solve the problem that you want to solve and to meet your modeling needs. So thank you very much. And with that, I will turn the presentation back over to Colleen.
We will have the slides available from this talk on our website where you can download them. And I think on that note, we'll wrap up for today. Thank you so much, everyone.
Thank you.